Hello, we're talking about molecular geometries or molecular shapes. The shape's very important in chemistry because the shape of a molecule determines its function. It can determine its reactivity, how fast the reaction takes place, and whether a molecule can do what it's supposed to do, particularly when we talk about biological molecules. And so we're looking at when we have some sort of central atom, like in carbon dioxide. That carbon is the central atom. And we want to look at the electron domains around the central atom. An electron domain could just be a non-bonding pair. It could be a single bond. It could be a double bond. Or it could be a triple bond. All those just count. They're just a single electron domain. So what we're using is something called the valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. That's a classical name of it. We could rename it the valence shell electron domain repulsion theory for what we're going to do here. And so if carbon dioxide, if those bond angles were more like this, and that bond angle were 45 degrees, there's a lot of repulsion between those electron domains. Remember those electron domains, be they non-bonding pairs or bonds, have electrons in them. Like charges want to repel. We look back when we look at atomic orbitals that we could put two electrons in an orbital by pairing up their spins, having them opposite spins. So we get two electrons to pair up in an atomic orbital. But for what we're looking at here, we can't. There's still repulsive forces between these electron domains, between the different pairs. And so we want to maximize the angles between the electron domains so as to minimize the repulsive forces. That's what valence shell electron pair repulsion theory is all about. So there's my CO2 molecule, if you will, and by taking a linear arrangement, that bond angle is 180 degrees, and we have maximized that angle to minimize repulsive forces. And so we can talk about the electron domain geometry, which describes those how the electron domains are arranged. The molecular geometry describes the atoms, how they're arranged. And if there are no non-bonding pairs of electrons on the central atom, the electron geometry and the molecular geometry are going to be the same. So that's true here. So it's both an electron domain geometry of being linear and a molecular geometry of being linear. Let's look at a molecule like BH3, boron trihydride. Now this is an OK Lewis structure. Now remember, boron can be electron deficient. And so we only have 6 electrons, right? Because that's all we have in the molecule to be able to draw. And this is an OK Lewis structure. And to look at it, you might think that's a right angle. But valence shell electron pair repulsion theory, or valence shell electron domain repulsion theory, says we want to maximize the angles between them in order to minimize the repulsive forces. So let's redraw that Lewis structure to make those bond angles, instead of being 90, 90, and 180 up here, make them where they're all 120. So now we've maximized those angles, and this is called a trigonal planar electron domain geometry. It's also a trigonal planar molecular geometry. The electron domains talk about how those domains arrange themselves. Here are the single bonds. The molecular geometry talks about how the atoms are actually arranged. And here the two are the same. Electron domain geometry and the molecular geometry. This molecule's, all four atoms lie on the same plane. All those bond angles are 120 degrees. So now let's look at the next molecule. Let's look at SO2. And we could draw a Lewis structure for it. Obeys all the rules. Here we've actually the sulfur has an expanded octet because we minimize formal charge. But we've got three domains. Each double bond counts as a single domain. The non-bonding pair counts as a domain. Those three domains want to arrange themselves actually to minimize those repulsive forces. So ideally we go back to this 120 degree type of angle. That gives us our electron domain geometry. The molecular shape is what we describe as being bent. Because there we're talking about only the atoms that we can see. Yes, there's this non-bonding pair of electrons that's pushing away, if you will, those double bonds, making the bonds between sulfur and oxygen. So the electron domain geometry is trigonal planar, whereas the molecular geometry is bent. So there are two different molecular geometries for this trigonal planar electron geometry. There are three atoms involved. The electron geometry and the molecular geometry are the same as we saw in the BH3. Here now, we've still got a trigonal planar electron domain geometry, but when you look at the atoms, it's now a bent molecule. The next one we want to look at involves four electron domains around the central atom, something like methane. We draw the Lewis structure. We would come up with a structure that looks like this. And to look at it, you would think those bond angles are 90 degrees. And that would be the case if that molecule were perfectly flat, that all five atoms were found in the same plane. However, by taking a three-dimensional shape, we can change that. Instead of all the five atoms being in the same plane, they can take a three-dimensional shape. And in so doing, we're actually coming up with bond angles that are 109.5 degrees. What we've now made is a geometric figure that's called a tetrahedron. it's got 4 sides to it. 1, 2, 3, and then the base would be 4. And so you could think of that as a three-sided pyramid, although I want to save that for the next one that we will look at. But there are 4 sides to that. It's a tetrahedron. And all those bond angles are 109.5 degrees. BSEPR. We want that bond angle. We want those angles between the electron domains to be maximized in order to minimize the repulsive forces. So that's methane. And so another way of drawing this structure, to try to show the three-dimensionality of it, sometimes you'll see this dash and wedge notation, where these 3 atoms, the 2 hydrogens and the carbon, they all lie in the same plane, whereas this wedge is trying to show a hydrogen atom and bond that's coming out of the plane of the paper, and the dashed line, the hydrogen, is trying to show it going away from the paper. And so if I were to do that with this model, here's a carbon, and they're the 2 atoms that would be in the plane of the paper. Those 3 are all coplanar. And then this hydrogen is coming out of the plane of the paper toward you, and that hydrogen is going away from you. So that's electron domain of 4, and that gives us our tetrahedron. Now there's another electron domain of 4 that I want to look at. And this is ammonia. If it's got electron domains of 4, that means it's got a tetrahedral electron domain geometry. But when you look at the atoms that are involved, this is what we're going to truly call, you see the 3 angles here. This is truly a pyramid. There are 3 angles, so we're going to call this a trigonal pyramidal shape. A trigonal pyramidal shape. Those bond angles are ideally 109.5, but we've got a non-bonding pair of electrons on this molecule. If this helps you to see it a little better, I'll use that little doodad to represent a non-bonding pair of electrons. It's actually pushing away. It's got a greater repulsive force than do the electron domains that are in the single bonds. And so it uses this highly technical term of squoosh. Sort of squooches down those bonds. And so if it's making them a little bit smaller, so actually the bond angles are a little bit less than 109.5 degrees in a molecule like ammonia. 4 electron domains, but one of them is a non-bonding pair. And so this is a trigonal pyramidal molecular geometry. The next one we want to look at is good old water. It's got 4 electron domains, the 2 non-bonding pairs, and the 2 single bonds. So if it's got electron domains equal to 4, that means the electron domain geometry is tetrahedral. But when we look at the shape of this molecule, if you looked at the Lewis structure, and that's legit, you'd think it's 180 degrees. But it's not, because electron domain geometry means that you're starting out with a tetrahedron. And so if we go back to that ammonia, there's our 4 sets of electrons. But now we've lost an atom, and we've got a second non-bonding pair on here. And so it's not linear. That bond angle winds up being bent. And so more accurate description, if we were to draw it, would be to have it looking something like this. And that bond angle actually, once again, it's less than 109.5 degrees. It's more like about 105 degrees, because those non-bonding pairs of electrons have a greater repulsive force than do the bonding electron domains. And so it squooches down that bond, if you want to think about it that way. So we're looking at electron domains equal to 4. We start out with methane. Electron domain geometry equal to molecular geometry because there are no non-bonding pairs. Ammonia, still a tetrahedral electron domain geometry, but now it's a trigonal pyramid. And water, still 4 electron domains. If I put those non-bonding pairs on here, it's still where you can see them. They influence the overall shape, which we now describe as being bent. But I want to go back to the SO2 molecule that we looked at a little bit earlier. If you'll remember, it was also bent. So this was SO2. But remember, it came from 3 electron domains. And so its ideal angle will be 120 degrees. It's less than that, like 116 or so. Whereas the water bent molecule is like 105 degrees. They're both bent, but they originally start out from a different electron domain geometry. So try to keep that in mind.